Okay, so you're going to get video pre-labs that you'll have to watch. And like I said, the pre-lab quiz will be taken from these. Not detailed. This isn't like exam one, I'm trying to bust on you hard. It's just sort of, you watched it and you can answer some basic questions. All right, so take notes during this. You should treat this like class. Turn off the other stuff going on around you. Don't watch this in the middle of a party. Take notes, rewind, watch stuff you didn't catch. You know, treat it like you're sitting in a classroom with me right now. Okay, so we're not gonna do much mass spectrometry right now, but the two chapters we're taking spectroscopy from are 14 and 15. Chapter 14 is IR, infrared spectroscopy, and mass spectrometry. Chapter 15 is NMR. You might be a little worried that we're going so far ahead. Basically, spectroscopy is put in the middle of the book because it's taught kind of all over the place at various universities in the United States. Sometimes it's very early, like in this class. Sometimes it's at the end of Orgo 2. Sometimes it's at the beginning of Orgo 2 or the end of Orgo 1. So the textbook writer just kind of puts it in the middle and you can do what you want with it. Okay. So first of all, spectroscopy is just studying the interaction of light with matter. Okay, so light, and when I say light, again, this is kind of like ethanol, alcohol out on campus means ethanol. Alcohol in a chemistry lab means groups that have an OH, molecules that have an OH group on it. So when a scientist says light, they don't mean just visible light. They mean all of the electromagnetic spectrum. Okay, so matter will absorb light of various types. If you think about a glass of water, clean water, it doesn't absorb visible light. If you hold up a glass of water, light goes right through it. But it does absorb infrared. It absorbs ultraviolet, it absorbs X-rays and gamma rays. You guys probably know that light is light. If you treat the wave property of light, you've got wave properties like wavelength and frequency. Wavelength is inversely proportional to energy, so the longer the wavelength, the lower the energy. Shorter wavelengths mean higher energy. Frequency is just the reverse of that, or the reciprocal of that. Frequency is directly proportional to energy. All right, so here's the spectrum. Like I said, we sort of see in here between about 400 and 700 nanometers. Some of you guys are young. If you have good eyes, you might see to like 370, maybe out to 740. I'm older. My lens has yellowed a little bit. It's a protein. It oxidizes. I'm probably at like 410 and 690. Okay, but generally speaking, 400 to 700. If you'll stick those in your memory, those of you who want to be doctors or biologists, like that's an important regime. And think about what we learn from just these 300 nanometers. We learn a ton about the world. We'll talk about that in a minute. But when you're looking at molecules, you want to use all the wavelengths, right? So we've got the ultraviolet, sort of 200 to 400. That can be dangerous, right? We get UV rays out in the sun. We get sunburn. We can do DNA damage with it. You've got the near infrared from about 700 to 2,000 nanometers, and that's water absorbs intensely in that area. The IR, when you think about like an IR camera sensing heat, you're really thinking about from 2 micrometers or 2 microns out to about 50, and then microwaves. The vacuum UV, we never have to deal with that because it doesn't penetrate the atmosphere. You've got X-rays, you've got gamma rays. You guys will not hopefully have encountered gamma rays. A lot of you will have encountered X-rays. So when I refer to light, I'm talking about gamma rays all the way down to microwaves, okay? Visible light, I will specify visible light. And I guess here, I want to say, just before, this is really important, all right? Basically, everything we know of the atomic world, the molecular world, is from spectroscopy, all right? These are too small for us to just see. So we have to study them and infer information, all right? Quantum mechanics plays into this a lot. Quantum mechanics, and it's an iterative process. Sort of humans discovered spectroscopy, and that sort of led to quantum mechanics. And then quantum mechanics gave a better theory of spectroscopy, better technology in spectroscopy led to refinements of quantum mechanics, and it's gone back and forth. But the the important thing to remember is that matter can't just absorb any wavelength, right? If you throw a ball at me, it doesn't matter how fast you throw it at me, it's going to bounce off of me. So you can't think about a molecule absorbing light like a ball and a person. If you throw a photon at a molecule, the photon may just pass right through the molecule. The photon can only be absorbed if the molecule can undergo a change in energy exactly equal to the energy of the photon, right? Basically, a molecule or an atom can't make change. If a photon hits it, it has to absorb all of it completely and make a physical change in the molecule, right? So I think the next slide has that a little better. No, it doesn't. I'll get back to that in a minute. So in infrared spectroscopy, well, it does. So in infrared spectroscopy, the physical change in the molecule we're looking at is a vibrational change. Okay, so, right, if you think about water, we always draw water like this. But water is not a static proton, oxygen, proton in exactly the same conformation. These bonds are stretching, right? So that OH bond is sort of doing this, like two balls on a spring. Both of these are doing that, and so, you know, the OHs can stretch asymmetrically, the OHs can stretch symmetrically. And then you can also get a bending, right? So if my fists are the protons, my body the oxygen, the molecule can do this. The molecule is always vibrating. But again, because of quantum mechanics, this is Orgo 1. I'm not a quantum theorist, so I'm not really qualified to go into the math of it. But the molecule can't just vibrate at any level it wants, energy level it wants. It can only vibrate at certain energy levels. That's what comes out of all the math. The math explains the natural observation that molecules' energies and the energies that they can exist at are quantized. Okay? So it can't just vibrate exactly at one frequency and then change to a slightly higher frequency. If it's vibrating at one frequency, it's got to change to a much higher frequency. And we call these energy levels. We represent this by energy levels. So this is the ground state. So the ground state is just where the molecule rests at a given temperature. So your glass of water, most of the molecules are in the ground state. In order to get up to the next vibrational level, it has to the molecule would have to absorb a photon that exactly equals this energy. That's going to be one wavelength. That's what's going to give material color. Right? If you think about why things are colored, it's because they don't absorb all of the light. They absorb one wavelength, and that lets other wavelengths through. You see those other wavelengths, and it has color. And so it turns out in water, for water, there is no energy level change that corresponds to the energy of a visible photon, right? From 400 to 700. There is one that corresponds to photons with the energy of 800 nanometers. We can't see that. There's also an energy change that corresponds to 150 nanometers. Again, we can't see that. So water looks colorless to us. All the wavelengths that we can see pass through water. Okay, so keep this in mind. This generally works for spectroscopy. Spectroscopy is always going to be going from the ground state to an excited state. There's going to be some energy difference between the ground and the excited state, and that's the energy of the photons that can be absorbed. By measuring the wavelengths that a molecule or a substance absorbs, we gain information about the substance. So there's a bit longer explanation here, and I'm aware that you guys you're going to have a lot to watch here, and this can be overwhelming. But again, this is just what I just said, right? You've got a ground state molecule, you apply energy to it, you transfer, the molecule is going to absorb the energy and go from a ground state up to an excited state. The difference in energy between the ground state and the excited state has to exactly equal the energy of the photon that gets absorbed, right? So molecules and atoms can only absorb certain wavelengths of light. We can also look the other way. We can excite the molecule and then watch it relax, right? If you pump a molecule up in energy, eventually it's going to relax back down to the ground state. When it does that, it has to emit a photon. And again, the photon that gets emitted has to exactly equal this energy difference between the excited and the ground state. So this is, for example, fluorescence, right? If you've ever seen something fluoresce, it's absorbed light, and then at some later point it emits light. In organic chemistry, we're going to have transitions. We're going to see transitions in the vibrational state of a molecule. That's going to correspond to infrared frequencies. It's the first spectroscopy we'll look at. We can pump energy into a molecule and break bonds. That's mass spectrometry. I'll talk more about that later in the semester. And then we can see emission of radio waves, this process, from excited nuclei. That's going to be nuclear magnetic resonance, and I'll also talk about that this afternoon. And then we're not going to get into this much until later in the semester, but molecules that absorb ultraviolet and visible light, so things that make us see color, these correspond to electronic transitions, going from one atomic orbit. If an electron goes from one atomic orbital to another, that's going to correspond to an ultraviolet or a visible photon. All right, so electronic transitions from one orbital to another are UV vids. Now, all of that might be overwhelming, and you might think, I'm never going to get this. You will. It will take some time, but you already do this. Right? You might be wondering why I'm showing what I'm showing. All of you, when you look at this, probably immediately had a thought of either I don't want any of these, or if you like these, which one would you want? Most of you would pick one of these, not all of them. So what are they? Well, they're cups of coffee, right? Like obviously they're cups of coffee, and some of that is you infer from the mug, but a lot of it you can infer from the coffee itself, right? Or the liquid itself. So we have coffee, as I like to call it over here, which is really dark, and then we have a milkshake as we go around over here. But you have a preferred taste, right? And you know that the lighter the color, the whiter it gets, the more milk or cream has been added. That is spectroscopy. You're letting light interact with the matter, and you're inferring information from it. And it's empirical in a large sense. You don't have to know about molecular orbitals to figure that out. You just have to have seen coffee before and drink coffee, right? So again, humans used spectroscopy long before we understood quantum mechanics. And people do spectroscopy without understanding quantum mechanics, but the spectroscopy leads directly to quantum mechanics, and quantum mechanics informs how we do spectroscopy. So just to remember, this is basically what you're doing. You're trying to put information in your head that lets you look at a spectrum, an IR spectrum, an NMR spectrum, and draw conclusions about the molecular structure. Right? That's what we're doing in this section. All right, so again, this just rehashes the types of spectroscopy we're going to do. We're going to start with infrared spectroscopy, and that's going to tell us what functional groups are present. All right, this is really important. As we go forward, when I say, hey, this is really important, this is something I might ask you on a pre-lab quiz. Infrared spectroscopy is primarily going to tell us which functional groups are present in the molecule. UV vis spectroscopy, which again, we'll look at later in the semester when we actually make some compounds with some color in the lab. So you're going to do reactions that change like a white substance into a red substance. We'll talk about UV vis spectroscopy, but that's basically going to tell us the state of the conjugated pi system, sort of how many resonance structures can you draw. And then the most powerful form of spectroscopy in organic chemistry is NMR spectroscopy. All right, NMR spectroscopy, in NMR spectroscopy, we're going to excite the nuclei, the magnetically active nuclei in the molecule, and then we're going to listen to them relax. And from that, you can get actually the connectivity of carbon and hydrogen in the molecule. So I'm an organic chemist, I like to make molecules. If you gave me one of these to use, I would choose proton NMR. All right, none of them by themselves are enough. The spectroscopic analysis process is very scientific. You have to fit all of the data to the spectra, and the spectra has to explain everything about a molecule. You can't just sort of discard one thing or another. We'll talk about that. That wraps up the introduction. 15 minutes. Geez, I'm sorry.